Welcome to BKW Physics today. Mr. McConley here. And I want to start with just a couple images off the internet. And I have some images here which are dragsters. And these dragsters are very exciting for people who like to watch this sort of thing. You know, they got fire coming out of them, they're just exciting, they're loud, they're aggressive, and they really get some people very excited. And they're also very fast. But what I want to talk about today is why does a dragster seem so exciting, yet if you took another vehicle and you drove down a big wide open highway or you drove across the desert at the same speed for a long time, that wouldn't seem nearly as exciting. It's kind of like this. If you're in your car and you're going down the highway, down the road at 70 miles an hour, at first the 70 might seem, ooh, that's kind of quick. And then after a minute or two, you're like, wow, it just seems like we're just going along. And it doesn't seem exciting anymore. Why is it so much more exciting with something like this? What's the difference? And that's what we want to talk about today, which is
acceleration.
It's acceleration. Thanks, Lucas. That's exactly what I'm looking for here. Now, this is one example. This is one example. Another example would be if any of you guys have been to a race which is on dirt tracks, and it's called sprint cars. Anyone been to a sprint car race? I see a few people raising their hands here. So if I quickly just search sprint cars, so that you can get the idea, a sprint car is one of these vehicles. Now these vehicles, again, I don't know, they seem kind of weird looking. They got like a wing on the top and they drive around on dirt. But what's amazing about these cars is in a very short track, a half-mile track, they can get way over speeds of 100 miles an hour. And it's all about the acceleration again. They can go from almost standing still to over 100 miles an hour in the length of a straightaway, and the length of the straightaway is much less than a quarter mile. Okay? So these cars are very exciting. They have enormous accelerations. But not only on the speeding up end of things, they also have accelerations on the slowing down end of things. So, let me just unplug this for a second. If you're in a dragster, or the sprint car, whichever one you want to think of, or you can think of your own personal vehicle, and you're driving down the road this way, this is the direction of your velocity. Okay? Now, if you're going down the road and you're speeding up, then your acceleration is also in that same direction. So if you're going faster and faster, I should make it look more like this. Start out slow, and then speed up and speed up and speed up. If you're accelerating, then the two arrows are going the same way. But if you're in the dragster or the sprint car and you're slowing back down, now you're still going this way, but as you slow down, your acceleration is pointing at you. So what is acceleration? Well, acceleration is how much or how quickly you're changing your speed. Okay? Now let me give you some numbers that can kind of back that up. So we're talking about acceleration here. And let's say that at a 1 second check, you're going 30 meters per second in one of these vehicles, a dragster or a sprint car. When we check in at 2 seconds, you're going 60 meters per second. And when we check in at 3 seconds, you're going 90 meters per second. You can see that the speed is changing and you're going faster and faster and faster. So when we talk about the acceleration, how do we say it? What do we say? Well, we say something like this. We say that your acceleration is 30 meters per second for every second. Can you see where I'm getting that from? So you're increasing your speed 30 meters per second every second that goes by. That's in this case, that's what your acceleration is. And that looks really awkward like that. Meters per second divided by seconds. So the way we usually write it is 30 meters over seconds squared. Because, we do the you know, the 1 over seconds, and we bring it up here. Anyway, we're left with seconds squared. So meters per second squared, that's your acceleration. Now, that's the idea of it. Well, in the physics reference table, the equation that goes with this looks this way. The equation is that acceleration is a change in velocity over a change in time. Acceleration, which is given the letter A, is a change in velocity over a change in time. Now, to just expand it out a little bit further to make it clearer, you could say that you're changing your velocity. You're comparing your final velocity compared to your initial velocity and comparing that to your change in time. All right? So, at the end of our example that I just erased, we were going 90 meters per second, and we started out at going 30 meters per second, and that took place over 2 seconds, so we could calculate an acceleration based on those numbers. And we'll do that in a moment as a practice. But before I do that, one other thing I want to throw in here are the units. So these are velocities, and if you're talking about units, Stephanie, help me out. What are the units for velocity?
Meters per second.
Correct, meters per second. So you got meters per second minus meters per second on the top, and on the bottom, time, as you well know, is in seconds. So if I simplify that a little, meters per second minus meters per second, apples minus apples gives you apples. So you got meters per second on the top and seconds on the bottom, which is that same complex fraction you just saw a minute ago. So our units for acceleration are meters per second squared. Okay? So that's just a quick unit thing. I like to always throw that in. So let's do an example. Let's do an example here. Say you're in your car, and your parents allow you to back the car down the driveway. You got a long driveway because you live in the country. Okay? And so you get in the car here, and you start backing up down the driveway. Okay? But as you're backing up down the driveway, you're getting pretty good at it. You've done it like 5 days in a row. You start giving it more throttle. So you're actually backing up down the driveway and you're accelerating down the driveway. You're going faster and faster as you back up down the driveway. So let's see if we can put some numbers to this. Say when we check in on the situation, your initial velocity is you're backing up, so it's going to be a negative number. We're going to say you're going 2 meters per second. Then you stomp on the gas a little bit and start backing up quicker, backing up, and now you speed up to a final velocity of 9 meters per second. All this backing up takes about 2 seconds of time, right? Well, what I want to know, if those are the facts, if you're backing up at 2 and then you speed up to negative 9, and it takes you 2 seconds, what is your acceleration? So let's take ourselves through. And I'm going to start right from scratch like you would want to do on a test. So, the acceleration is the change of velocity over time. The acceleration is the final velocity minus the initial velocity over time. The final velocity is a negative 9. Now watch this. Don't get fooled here. Minus a minus 2. See, because it's minus the initial velocity, but the initial velocity is already negative, so it's a minus minus over 2 seconds. Well, then on the top, because these turn into a positive, then this on the top is 7 meters per second, and this is 2 seconds. It turns out to be a negative 3.5 meters per second squared. And you'll start to get a little bit more comfortable with what those acceleration numbers mean as we do more problems. But that's not a really big acceleration. That's pretty moderate acceleration. Now, the one other thing I want to point out before we wrap this up today is that you can use this equation in a different arrangement for different situations. Like, what if I say this? What if I tell you as another example, back to the sprint car again. I tell you that the sprint car has an acceleration of 12 meters per second squared. And I tell you that when you come out of the corner with the sprint car, you're going to be going kind of slow. You're going to be going at an initial velocity of 5 meters per second. But then, once you see the guy with the green flag drop the green flag, you're going to punch the throttle and the thing's going to, it's going to accelerate really quick and you're going to go flying down the track. And you're going to basically hold the throttle for full throttle for a time of 3 seconds. Well, I want to know, at the end of the 3 seconds, how fast are you going to be going? What's your final velocity at the end of the 3 seconds? Well, let's back up to this equation here. And you should probably rewrite it in your notes. So you got your equation here. Acceleration is final minus initial over time. But this time, you're looking for the final velocity. So I'm going to rearrange first. I always like to rearrange the equation before I put the numbers in, remember. So I multiply both sides by t. I got TA or AT on this side. I got VF minus VI. And then I add the VI to the other side. So I got VI plus AT or plus TA, whichever way you like to say it, is equal to VF. This is actually another equation in your reference table. It's the same equation, they just rearranged it for you. Okay? Let's plug in our numbers, see what we get. So we're starting out at 5 meters per second. We're going to accelerate at 12 meters per second squared for 3 seconds. Can you do that in your head? What do we got? We got 5. What's the multiplication give you? 36. 36 and 5 gives you 41. So we're at a pretty robust speed of 41 meters per second at the end of the 3 seconds with that sprint car after it accelerates down the track. So this is 2 ways you can use your acceleration equation. Until next time, physics.